Hello, everybody, and welcome to Creation Myths. I have a super fun show tonight. If you are a giant nerd like us, this is going to be super fun. Otherwise, I can make no promises. As always, I am just checking that I can hear myself on YouTube. I can. As always, if viewers, if you detect any technical issues with me or my guest, just let me know in the chat. I'll be keeping an eye on it, and I'll make sure that nothing goes too far astray here. So tonight we have, like I said, we have a really fun show, and I have been looking forward to this for over a month because we're going to do a lit review. And since I got my hands on this paper, I've been looking forward to talking about it. So my guest tonight, before we go any further, is Dr. Zach Hancock. Zach, take a minute, introduce yourself, tell everyone what you do and where to find you on YouTube.
Yeah, so I am a postdoctoral researcher at the University of Michigan. My research background is in population genetics and phylogenetics. I do mostly modeling nowadays, but once upon a time, I did some empirical work on amphipod crustaceans, a lot of popgen and amphipods. And on YouTube, I do a little bit of a mix of sort of evolution education stuff, also some history of science. And every once in a while, I will also do some creationist debunking things. And that is how I came to meet Dan as well. Yeah. So that's me. You can find me at @TalkPopGen. That's my YouTube handle.
And that is linked down below in the description. Do not walk, run. Click on that. Hit subscribe. If you enjoy what I do, you will enjoy what Zach does. So go down, click on that, hit subscribe. Enjoy Zach's excellent work. So just a quick programming note from me before we go any further is I recently enabled channel memberships. So if you enjoy what I do here, I encourage you to be a channel member. And even at the lowest level, the benefit you get is early access to all of my pre-recorded videos. I release videos every Wednesday night. Sometimes they're live, like here. Sometimes I've recorded them and uploaded them ahead of time. If you are a channel member, you get to watch it whenever I upload it. Sometimes that's like Wednesday afternoon instead of Wednesday night. And sometimes it's earlier in the week or the week before. It kind of varies. But I've been trying really hard to stick to this every Wednesday schedule. And so far, so good. So if you want early access to things, consider doing that. And I appreciate the people who have already done it. So that out of the way, doing the plugs and everything out of the way, let's talk about what we're going to cover tonight. So I am going to just I'll share my screen and show everybody what we're going to do tonight. Now, the thing that you're going to see on screen is my copy of this paper, the PDF of it, that is full of highlighting and notes. So you're going to see my highlighted version, and we'll talk about some of those highlights. There's probably too much for us to cover in a single show. So what we are covering here is this paper by Dr. Rob Carter from the proceedings of the 9th International Conference on Creationism, which was held in 2023 at Cedarville University. So let me share my screen. This is me being really good at live TV because I have to pick the thing to share because I didn't do it ahead of time. So let me share my screen here. Window, that, share. And we'll just pop that right up. There we are. So here's the paper we are talking about. It is called Genealogical versus Phylogenetic Mutation Rates. I'm going to zoom us in a little bit here. I'm going to make it a little bit bigger for us so that everybody can read what we're doing. That's a little bit better. Now, this is important because this is a long-running conversation in the young Earth creation extended universe. This idea that we can take short-term mutation rates measured parent to child, and we can extrapolate those backwards to calculate when common ancestors for different parts of the human genome existed. And when you do the creationist version of population genetics, you can get yourself a number that is in the 6,000-year range. And Dr. Rob Carter, the sole author here, has spent a lot of time recently on his YouTube channel going into this in a number of videos. And I will pat myself on the back a little bit because me and him have a we're frenemies. And a lot of his videos have been responding to me on this topic, occasionally named, sometimes not. So I like that he put this out there in a more formal way, and that allows us to really see what the long version, the technical version of his argument is here. So what we're going to do is we're going to go through some of the basics of this, and then we're going to talk about what Carter did and what his argument is, and then we will talk about so many of the problems. I won't say all because we only have so much time, but we'll see how far we get.
This paper was like so clearly targeted at you. I just kept waiting to see your name appear at some point that's like referenced in this paper.
There's a few places where he's like, some skeptics, and I'm like, that is a thing that I wrote. Like that next sentence is a thing that I have said to you, Dr. Carter. So here we are. So Zach, you are the expert here. And for people who are not super familiar with Zach, so like, I'm an evolutionary biologist. I'm familiar with population genetics. I know more pop gen than your average person, and probably more pop gen than even your average biologist. But Zach is a professional. Like, that is the thing he does. So before we go any further, Zach, are there any kind of major principles, major topics that everybody should be familiar with before we dive into Carter's argument here?
Yeah. So there's several things that he brings up that we should be sort of familiar with, and that, and to many respects, this entire argument is based a little bit on a false premise, and we can talk about what that is. But the contention, and he makes a reference several times to standard population genetics. He references this several times, and so I think it's important for us to know what he's referencing versus the way he's actually using that. And what he's talking about is whether or not the rate of substitution is equivalent to the mutation rate. And this particular idea goes all the way back, believe it or not, to Sewell Wright in 1938. This is a really, really old idea. And Kimura often gets the credit for it, but it actually goes all the way back to Wright. And it's maybe one of the most misunderstood ideas among the general public, I think. And this is like, not to knock Wright and Kimura because they were brilliant people. The key is that we're missing a couple of important terms. So without like actually doing the math, effectively, if you take what is the rate of substitution, and importantly, substitution means that there's a mutation that originally arises in one individual and then spreads to every single individual in the population. Once that happens and everyone has it, it has now been substituted or fixed. Okay. So we might be interested in what is the rate of substitution. And generally, when we care about this between two species. So we're like, how much divergence is there between two species? So we're actually interested in the rate of substitution between them. You can't actually tell substitutions within a population because like it's substituted now. And we'll talk about why that's relevant here later on, I'm sure. But effectively, what you need to do is you set the rate of substitution equal to the number of new mutations that enter into the population every generation. That's just the population size times the mutation rate. And then there's some rate at which, or some probability at which any of those mutations go to fixation. If that probability is exactly equal to chance, if it's just random genetic drift driving it, then it's equal to 1 over the population size. Well, it just so happens the number of new mutations that enter the population is the population size times the mutation rate. So you've got the population size and then 1 over the population size, those cancel, right? And then that leaves you with the rate of substitution is equal to the mutation rate. Okay, so far so good, but there's a few key things that we need to understand here. One is that this rate of mutation is not the pedigree mutation rate. That is not what Wright meant it. That's not what Kimura meant it. That's not what any population geneticist has ever meant it. It is very specifically the neutral mutation rate. That means that is an allele that is not being impacted by selection at all. That's the only way for this to work. Because not only does that need to be neutral, the rate at which it, or the probability at which it goes to fixation has to be equal to 1 on 2n. And for it to be equal to 1 on 2n, that means it's drifting to fixation. It's not being dragged by selection. It's not linked to something and being dragged by selection. And also importantly, there's like some other demographic things we need to think about, like that there's not fluctuating population sizes. So then 1 on 2n is not constant through time. And so they don't cancel. There's like a couple of other interesting things to consider. But whenever he starts talking about standard population genetics and he's like trying to appeal to, like, he makes it sound like it's like textbook orthodoxy that he's appealing to here, right? There's nuance to this, and there was nuance for a very long time that we've understood, and we don't use the pedigree mutation rate. We use the neutral mutation rate, which is very, very different, and is actually much closer to what we would call the phylogenetic rate. So the rate that you would estimate between species, because then selection has already weeded out any deleterious mutations. They're not there anymore. So what is actually accumulating do tend to be the neutral mutations. And then you get this sort of linear relationship between time and divergence. So I think that's like maybe a real big key sort of background pop gen we need to be aware of going into this is the population genetic understanding. And then as we talk about Carter's, representation of it, we'll see why it diverges from that.
And just to add just a fun little bit onto that, this obsession that creationists have with the pedigree mutation rate is a relatively recent thing, because it's not all that long ago that we didn't actually have DNA sequencing that was cheap enough and fast enough to be able to generate a lot of like parent offspring sequence data that we could then compare this rate. So this kind of stuff goes back to like 2015, and there's a 1998 is the first time that's the earliest paper that creationists latch onto, and then there's another one from 2015, and it was Nathaniel Jeanson that kind of started this whole thing. And then basically every professional young earth creationist and the amateurs that just kind of parrot what the professionals say, they're all basically cribbing what Jeanson is doing here, that go back to his papers in Answers Research Journal and his two books, Replacing Darwin and Trace. That's kind of the pardon the pun, the pedigree of this argument is that it goes back to a 1998 paper and a 2015 paper that Jeanson latched onto, and then everybody else basically just repackages Jeanson's numbers directly or his techniques applied to other situations. And that's what Carter is doing the latter here. He's doing the Jeanson techniques on simulations rather than referencing these old papers.
Yeah, and I think that maybe one additional important sort of background that we need to know going into this is at least some really brief understanding of what coalescence is.
Yes,
because he's basically going to be making this argument, right, that mitochondrial Eve or Y chromosome Adam or whatever lived too recently in the past. And if that happens to be the case, then the evolutionary timeline is overturned. But he doesn't seem to understand what coalescence is. And he doesn't seem to understand that coalescence is not the origin of species.
Yes.
And so I understand coalescence is a complicated idea. Like, people struggle with it, but I think we can make it really, really simple if instead of thinking of coalescence, we think about fixation. So imagine a mutation arises in one individual on one chromosome. Okay. And that mutation is destined to go to fixation, such that everyone eventually is going to have that mutation. What that means is now everybody at the point in time that mutation is now fixed, all descend from one individual in one haploid genome from where that mutation first arose. So that's fixation forward in time. Backward in time, it's coalescence, right? So, but remember, it arose in a population in one individual, and there was a whole population of individuals with all their own variation that just happened to get lost. Now, this can be genetic drift can drive this, as we already know, or selection can drive this. Either of these processes are capable of driving fixation, but at no point was the population like, is this the emergence of a thing? Right. Is at no point was the population collapsing or like changing in size. It doesn't, like, the population can be completely constant and could have existed indefinitely prior to this, right? It's just that it's a brand new mutation that went to fixation. So coalescence is just fixation backwards in time.
That time to most recent common ancestor only tells you that very narrow piece of information. It doesn't tell you what the population size was at that time. It doesn't tell you that it was the origin. It doesn't say there was a bottleneck or some other weird thing going on. It just tells you that one very small, very specific piece of information. Before we go, I just have a couple little housekeeping things. Want to thank Charles for your membership. I appreciate you. Thank you. And also, Nancy, thank you for your contribution. I appreciate it. Thank you. And welcome everybody. It's I've seen people popping in as we're getting going. There's over 50 people here listen to us nerd out about population genetics, and let me tell you, that just warms my heart.
Mine too. Mine too.
Okay, so that's kind of the background of the concepts that are at play here. We have the human population as it exists now, and we have this concept of coalescence. So we look at genetic diversity within all of humanity, and we say, how long does it take to coalesce? What's that time to most recent common ancestor? And specifically, we typically, when we're dealing with creationists with this, we're talking about the mitochondrial DNA and the Y chromosome. So I think that gets us. Is there anything else you want to kind of foundation you want to lay before we get to the actual paper?
Let's go ahead and jump in.
Let's talk about this paper. So the big idea with this paper, I'm going to start, and then I'll let Zach kind of add some detail here. But the big idea with this paper is that Rob Carter is trying to address the argument that I and lots of other like real biologists make when it comes to the creationist math on this stuff, that you can't just take that neutral mutation rate and project that backwards in a linear fashion and say that explains all the genetic diversity that we see. And therefore, because that is a relatively rapid rate of mutation occurrence, that you have your most recent common ancestor in the recent enough past that it's within the 6,000 years of a young Earth biblical timeline. And so what he attempts to do in this paper is use various simulations to show that even with natural selection operating, it doesn't slow down, I'll use the phrase, slow down the rate enough to get you the time to most recent common ancestor that's outside the biblical time frame. That is his claim, and that is 100,000-foot view of what's going on here. He's trying to refute this idea that people say is, well, sure, there's drift going on, but there's also selection that reduces the rate at which things reach fixation. Therefore, you push that time frame back into the tens of thousands or hundreds of thousands of years, and now you've refuted the young Earth timeline. Zach, feel free to take it from there.
No, I think
we can do more detail or just go through it.
Yeah, I think that's a pretty good high level take on that. I will just simply add that even if we granted them that the most recent common ancestor was 6,000 years ago, it says absolutely nothing about when humans originated. All that would mean is that the human effective population size is minuscule. It would mean our effective size is like really, really small, much smaller than like actually the genetic diversity that we possess would seem to indicate. So, but again, because coalescence is not the origin of species, it's just the last time when you had fixation. That's literally it.
And I will say there's a trend in young Earth creationism where they'll make different arguments at different times that if you put those arguments side by side, they are contradictory with each other. And this is an example of that, where they talk about, we have this amount of diversity in a short amount of time, but they'll also say things, and they'll say like the mutation rate can explain that, but then they'll also invoke like created heterozygosity, because they can implicitly acknowledge that the rate at which mutations occur actually doesn't explain that. They have to have this other mechanism at play to generate the amount of diversity that's actually present. Yeah. So we're going to not worry about that tonight. We're going to take this argument kind of on its own, but this argument that we're dealing with tonight is actually directly contradictory with other creationist arguments that they make to explain kind of extant human genetic diversity. And again, thank you, Ian. I appreciate your generosity, sir. So Zach, should we go through the paper and talk about what Carter did and why it's just an absolute dumpster fire?
Yeah, let's do it.
Okay. So as you can all see, we have the I have the paper here pulled up. I hope the font is large enough for everybody to read. I can actually make it a little bit larger here. Not too much larger, but I can make it a little bit larger for everybody. Let me do this real fast. Maybe I can zoom in a little bit more. Yeah, there we go. Okay, I hope that's big enough for everybody to see. But I'll be reading places that are relevant when we get there. So let's just go through this. What I've done is I've highlighted things and I've left little notes to myself, and I'm not going to go through all of the notes that I've left because there's just too much to cover. We'd be here all night. But there's a couple really big ones that just are like absolutely gobsmackingly obvious errors that we ought to talk about. So as I scroll through this, Zach, feel free to stop at any point and we can talk about whatever. I'm just going to jump down here For me, my first one is on page 169, which I believe is this page. Yes, right here. And we were talking about this beforehand. So Carter here cites a number of different studies, basically genealogical studies, which are looking at parent-offspring pairs and the number of mutations that are different between them. And then he takes that as the per generation mutation rate. And there's a really interesting thing with these studies, because some of these studies cover a single generation. You've got parents and you've got kids, and you can see how many differences there are. Other such studies are what they call deep pedigrees. So it's multiple generations, and you might have, 200 something individuals in the present, and we know they share like a great, 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 great grandparent going back however many generations. And so you can actually calculate over that kind of, decades to centuries time frame what the mutation rate is that we're looking at here. And what creationists have noted repeatedly, Jeanson has noted this in Traced, Carter has noted this elsewhere, is that when you do these things with more than one generation, the rate you get is somewhere in between the rate that young Earth creationists like and the long-term phylogenetic substitution rate. It's somewhere in between. The reason being because processes like natural selection weed out variation over those generations.
Like selection is slowly purging mutations.
It's almost like you can draw a curve that asymptotically approaches the long rate, right? Or the slow rate. And I just want to call attention to this one right here. This paper from 2002, it's this Connell et al. 2002, looking at 225 individuals, and collectively in this pedigree, there are 345 what we call generational events. So that's parent-offspring transmission events, right? And what they found was a rate of 0.029 mutations per generation, which is 16 times faster than the phylogenetic estimates that Carter is citing here. Now, here's a really interesting thing about this number. I did something that Carter does not do in this paper right here, which is take that number and say, okay, if it is that many mutations per generation, and 0.5 mutations per generation puts mitochondrial Eve in the recent past, which I interpret to mean a biblical time frame. That's why he's citing that. Right, it's 0.5 per generation gets you approximately 6,000 years. If you take that at face value, which sure, let's give that one to Carter. This rate that is anomalously fast puts your time to most recent common ancestor approximately 100,000 years ago. So this is a trick that Rob Carter does not just here, even though he does it frequently here. He also does it in his other work, where he cites a thing and says, this is weird, and then doesn't do the full explanation. And the reason for that is he will cite seemingly anomalous results that still refute the conclusion he is trying to prove to the reader. So here he's saying, hey, look, even the evolutionists, they get this study that's 16 times faster than it should be. Okay, how many years, Rob? How many years does that get you? It's still 100,000 years. So what's the problem?
No, and he's actually cited a couple of these things incorrectly. I want to point out that several of these numbers are wrong. For one, the Madrigal et al. 2009 is a paper that does not exist. He actually means to cite Madrigal 2012. The 0.5 per generation rates that he's citing is not per generation, it's per million years. Which is obviously quite a bit different.
Amazing.
It's a few orders of magnitude off. The same thing is also true where he says they also summarize prior studies which claimed mutation rates ranging from 0.12 to 1.2. Again, he says per generation. That's not per generation. That's per million years. Again, you can check out that. Yeah, you can check out that study. He's using that incorrectly. So when you actually use the rates that they estimate, and again, these are pedigree rates, right? So which are, as we would say, are faster than the phylogenetic rates, and they are actually taking into account a lot of mutations that will not fix, right? That selection will purge them. So if you tried to estimate the coalescent ancestor from them, you are going to underestimate the time. So I just want to make that clear. But like even granting them these rates and making sure that it's the actual rates at the paper side and not the rates that he's incorrectly citing, you're still like, even with the fastest one I could find was still greater than 30,000 years ago. And that's 5 times greater, right, than the young Earth creationist time frame would allow.
And can we just all take a moment to appreciate this line that I've highlighted here on the bottom left of that column. Excluding the one study that discovered 0 mutations among 292 generational steps. That is just like, we're also not going to count the one that makes my numbers that makes my math really hard. We're just going to not count that one.
Yeah.
Because if you look at 0 out of 292, right? Like, we got 345 and it's 0.029 per generation. So, like, you know what? Like, I don't know, Rob. Maybe you should have put that one in your math and seen what happened there. You know, probably shouldn't just randomly exclude studies without providing a reason why.
Yeah.
Just in general. That's a red flag for me.
No, it definitely is. And it's also, the misciting of the rates themselves obviously just inflates the ages, which is, you know, obviously a large problem. And if you actually go back to these original studies, yes, they talk about them being a lot faster, but they don't dramatically change the time to, or they don't make the time to most recent common ancestor within 6,000.
Yeah, you can't do it. Jumping down, again, I've highlighted a lot here, but there's only a handful of things I want to highlight because, man. So, Zach, stop me if there's anything you want to talk about on pages 170 or 171. Obviously, I've highlighted a lot of things, but it's more just like, for me, in order...
Yeah, I've got just like one quick thing on 170. This is just like a me being reviewer 2 kind of thing. Because, I mean, here we are. So on the paragraph, he says the rate of fixation is also strongly affected by population size. If that happens to be the case, then the substitution rate doesn't equal the fixation rate, like by definition, right? Because the only way it can be is if the population size is not impacting it, because they cancel out because the rate of drift is 1 on 2 in, and then the number of new mutations is in. But if it's being strongly impacted by the population size, and those things aren't canceling, and so you can't actually use the rate of fixation as equal to the mutation. So he's just like literally contradicting himself by pointing this out.
But he said that he's just using what's the phrase? Basic population genetics. What was the phrase he you know?
Yeah,
just basic population genetics, Zach. Come on, we're just using basic. Everyone agrees. Doesn't matter. So jumping down here, starting at the very bottom of page 171 and then going into 172, he talks about one of my favorite papers of all time. This, I don't know how to pronounce this author's name, but Soares et al. 2009, which is great. Because what they do is, in that paper, they calculated the long-term substitution rate for humans, starting with human-chimp divergence based on all the evidence we have and saying, here's what this looks like. But the model that they generated, the equation essentially that they generated for this explicitly includes selection. And I should say this is for the mitochondrial DNA. But then what they did is they didn't just leave it at that and say, human chimp, here's the rate across those. They use 6.5 million years. They didn't stop there, because what they then did is they did this thing called phylogenetic cross-checking, where they also looked at that rate of divergence between human populations with a known divergence time. And the thing that I love here is some of the numbers they used. They checked, for example, the first movement of Homo sapiens into Europe, and they also used the settlement of Japan, which are based on archaeological records, right? But they also used events within the last 2, 3, 4,000 years that are based on like recorded human history. So we're talking about like settlements into like Pacific Islands. And it was the Pacific Islands and the Canary Islands were the 2 big ones. And those were both within the last few thousand years. We know when those things happened. It's within the biblical time frame. And it's even in a biblical time frame, it's post-flood. Like, nobody disagrees on when we settled the Bismarck Islands. Nobody disagrees about when we settled the Canary Islands. So what these authors were able to do is, by looking at the sister population and then the offshoot island settler population, we could figure out that rate over just a few thousand years. And what they found was that the rate that they observed rate in these divergent human populations directly matched what they would project based on their calculated model incorporating natural selection. Now, Rob Carter goes out of his way to misrepresent these findings in several ways here. Yeah. First, he plays the ever popular, well, they're just assuming human chimp common ancestry card. And no, what they did was very robust. They're looking at a lot of evidence to establish that 6.5 million year divergence date for the human chimp common ancestor. They're like, I don't know if Rob's read that paper because they really spend a lot of time on like, here's how we got the 6.5 million years. There's a thing that science writers do, right? Is we say we're assuming, which means we're taking this other work at face value and we're not going to like worry about it ourselves. But there's no assumption of 6.5 million years. That's built on literally centuries of data. Right, there's no assumption there.
There wasn't a that
right.
comes from the evidence. That's why
right.
we say that that's the age. It's also very interesting to me that he never mentions things like D&DS ratios here. And so like if you want to know if selection, if like purifying selection is acting, you just do a very simple D&DS ratio. And this is the ratio of non-synonymous substitutions over synonymous ones. And if you happen to find that that ratio is equal to 1, then you know this region is evolving completely neutrally. You've got just as much non-synonymous as synonymous. But very often this ratio is much, much less than 1 because non-synonymous substitutions change the amino acid and that can change the protein, right? And if the ratio is less than 1, then that is a strong indication that purifying selection is acting. And if you look across the mitochondrial genome, that ratio is always way less than 1. It's much more less than 1 than even in the nuclear protein coding genes. So there's very strong purifying selection in the mitochondria.
And that's because the mitochondrial genome is small and dense. It's very small. Most of it is genes with relatively small intergenic and non-coding regions. So the likelihood of a mutation landing in a gene is quite high. And then within that gene, you have approximately better than a 1 in 3 chance of that, or about a 2 in 3 chance, give or take, of that mutation. It's better than 2 in 3 of that mutation affecting an amino acid. So that's why the D&DS ratio in mitochondria is so low, below 1, compared to the rest of the genome, which is largely non-coding. The other thing Carter gets wrong here is the line that I've highlighted, where he says the authors were able to estimate the timing of specific historical events in human history, such as the settling of the Canary Islands and remote Oceania. No, the authors didn't estimate those things. They didn't say, according to our rate, here's when we think these things happened. We know when those things happened. What the authors did is basically reality check of their math. We know when this thing happened. Does our model give us the date that we know is correct? Right? It wasn't like we're using he's got the directionality wrong of what they did. Yeah. What he's saying here is the author said, here's where the Canary Islands were settled based on our model. That's not what they did. They said, we know when the Canary Islands are settled. Is that what our model says? It was a way of verifying if their model is accurate. Yeah. And they did this across a number of events spanning tens of thousands of years to check the accuracy of their model. And wouldn't you know it, it was spot on. Everything they checked was consistent with their model. So Carter's just he's getting this wrong. I don't know if he's doing it on purpose or what, but he's describing this paper incorrectly, and it's very frustrating.
Yeah. I have something quick on 171.
Oh yeah. I have a few things there.
I also have a few things, but I'm trying to not dwell too much here. But there's the section where he's talking about there's no way for natural selection to slow down the rate of genomic change without seriously risking extinction. What he's assuming here, one is that selection is always hard. So selection can be hard or soft. And for the audience that may not know the difference between these, so selection can either be acting on absolute reproductive output or absolute population size. In this case, if you have lower fitness, that means that the population is actually declining in size. If you have higher fitness, then the population is literally growing in size. That's hard selection. But selection can also be soft. And in this way, soft selection is relative selection. I had a commenter on a video that actually put a really nice point on this. And he stated it as soft selection is like, I don't have to outrun the tiger. I just have to outrun you. Right?
Bingo.
So it's not actually about absolute survivorship. It's about, can I survive better than a neighbor, right? It's relative. And so in this sense, fitness is not, doesn't actually depress population size. It's all relative. So it's very, very important to understand that selection can be sort of soft and in a competitive relative way, or it can be hard. And these are very different things. And in soft selection, you don't have concepts like genetic load, right? You don't have concepts like selection driving populations to extinction because it's all relative. So I just want to point that out. This is a really important sort of point that I've never seen a creationist properly like deal with, that selection doesn't have to be absolute. It doesn't have to be hard.
And I'm gonna just piggyback off of that, because that was a note that I had for later on. So I'm just gonna jump briefly all the way down to page 178, because it is a small thing, but it is one of the things that I noted that invalidates what Carter is doing here. Because remember, what he is attempting to show is that selection is not removing mutations at a rate that is sufficient to push that coalescent date outside of the young Earth timeline. One of the limitations here is that by using hard selection, he consistently invokes the risk of extinction. You can't have selection that's too strong, i.e. that's removing too many mutations, because then the population goes extinct. He actually was very explicit about this right here on page 178, right at the end of the paper. These mutations reduce reproductive output, but never subject to selection in a way that is modeled here, e.g. via an annual risk of death. The way that is modeled here via an annual risk of death. So he's saying here, the way he is doing selection is if you have a bad mutation, you die. That's how that mutation is removed from the population. But that's not the only way it can work. Yeah. You might have, with your bad mutation, one kid, whereas your neighbor without that mutation might have 2 or 3 kids on average. That's still selection against that allele. But Carter's not doing that. He's just saying death. And if you restrict your mode of selection to death, then yeah, if you have too much selection, your population goes extinct. But that's not how the real world works. Yeah. So he's artificially limiting the amount of selection that can be tolerated here by only modeling selection via death and by not having these relative competitive advantages and disadvantages.
I would say he's doing something even worse. So go to figure 3. It's even worse than this, because he's not even correctly modeling hard selection. So and I think I know why.
It's figure 3. Yeah, here we go.
This is figure 3. So, and I think I know why Mendel's accountant works in the way that it does. So if you can, so notice on the right side of the y-axis is population size, and the blue line is population size. So notice it does not change. The other side of the y-axis is fitness, and the red line is representing fitness. But the population size does not change. So if this is truly hard selection based on survival, then as fitness goes down, the population size should go down. And in fact, the rate at which that fitness is declining, that population size would go extinct in a couple thousand generations. It would go extinct within the biblical time frame, right? And I think that is why that they're modeling it in this way, because if you were to actually model absolute selection in the way they're talking about they're modeling it, then we should already be extinct, right? And I've tried to make this point in previous videos, but like if you take the current like mutation rate and you assume a genetic load model, then it creates a paradox, right? That we literally shouldn't exist, and yet here we are. And so there's clearly other processes at play that they're just trying to ignore by like creating this like really, really artificial simulation model. So I just wanted to point that out, that they're not really even doing a truly hard selection model.
He describes it as a hard selection model, but then that's not what's happening in the simulation. Yeah. And to be clear, just for the audience, to be clear, what we just described invalidates everything, but we could just stop here and like nothing that Carter says is valid because of this problem. Like we could just be done. We could be done. We're not going to be done because there's so many more problems, but we could stop. Like that's it. We could stop there. So let's see.
Yeah. So real quick, the last one on 171, and then I'll just move on.
170. Here we go. 171.
He says, third, by invoking selection, all mitochondrial molecular clocks could suddenly be wrong.
Yeah.
And I
love that paragraph.
I want to make it clear for everybody in the audience what a molecular clock is, how we use it. And so basically the molecular clock is a very simple prediction, and it predates even the idea of neutrality. Okay. So the molecular clock works like this. If you could plot time on the x-axis and then genetic divergence on the y, if those things are linear, if it's just a linear relationship, the molecular clock works. Doesn't matter if there's purifying selection or not. You just need a linear relationship, right? Now, that doesn't mean that the pedigree mutation rate equals the substitution rate. That's a whole different thing. Now, it just happens that those are related ideas, and that if that happens to be true, then you will also get a molecular clock. But if purifying selection is at work, purifying selection, especially if you're like thinking about a protein that's the same in lots of organisms, like the mitochondria does the same thing in every critter that has one, right? In this case, purifying selection is acting largely the same. It's removing the same sorts of mutations. And so you get this new equilibrium mutation rate, what we would call like the long-term substitution rate, and that can be linear. It can be a linear function of time and divergence. That's a molecular clock. So selection doesn't invalidate the molecular clock. Positive selection invalidates the molecular clock. So if you have adaptive evolution, that will jump you off of that linear line, and then that would invalidate it. But other than positive selection, no other kind of selection invalidates the molecular clock. So I just want that to be clear that he's just dead wrong on this point.
That seems like a trend. That is just like fairly basic population genetic stuff. We're getting errors that would cause a student to like fail an undergraduate class. You would get these questions wrong on an exam. There's one that I think we're both saving and looking forward to that I can't wait. We'll get there. So excited for it. Okay, so let us continue. That was page 171, 172. There's so much wrong here, but we don't have time to cover everything. There's so much fun stuff here. So let's pop down. I just want to look at 174 because it's in the figure here. It's that's 173. Here we go. I think this is really interesting. So what he has here is he has the retention on the right y-axis. We have the percent retained for mutations, and then that's the blue curve. And then we have the total mutations, the number of mutations that appear. That's the orange line, and it's a linear, per generation. We got population size across the x-axis here. And the interesting thing here is that he describes in the legend for this figure, strong drift measured here as allele retention, which will eventually translate into allele fixation, is evident in the smallest populations, but drift slows to a crawl after the population reaches a few thousand individuals. Now, that second part, like drift is most prevalent as a driving force of the what you see in a population's genetics, that is most prevalent in small populations, and it loses importance, it decreases importance as the population size gets bigger. It is true. I find it really interesting that he talks here about genetic drift measured here as allele retention.
Yeah,
because typically we think about it the other way, that drift is the random loss of alleles. As if you have two alleles in a gene, right, and one of them randomly reaches fixation, then what happens to the other one? It is lost from that population. So the effect of drift, he's putting it here like drift maintains, but the effect of drift is that most mutations are lost from the population. That doesn't affect the math for the reason that you talked about before, where the population sizes cancel out. But it's kind of an insight into how he's thinking about this and how he approaches it, that it's always like, how can I shovel more mutations into this, right?
Yeah, this is this whole framing of things like percent retained and also looking at total mutations. This is very strange. We don't generally think about this in Pop Gen. So like, I was very confused if he meant percent retained is literally like percent that are still polymorphic at the end of the simulation, or if he means the percent that are fixed at the end of the simulation. This was very confusing to me.
Clear. I interpreted it as like X number of mutations occur per generation. For a population of a given size, how many of those mutations are at a frequency greater than 0 is how I interpret it. What's still present.
Okay.
But if retained means fixed, then it's a totally different thing, and it's not clear what he means.
Okay, so so if it's percent retained means polymorphic, right? So that's a measure of like genetic diversity, then this plot is wrong. It's like it's backwards, right? And it also tells us something really important about his failure in modeling here. And we can get into like the nitty gritty of the methods, but we don't have to. The basic point is that he runs a bunch of different population sizes, and you can see that on the x-axis here. But he runs them all for the same number of time, same number of generations, like 10,000 generations. but it takes time to build up an equilibrium amount of diversity. And in fact, the amount of time it takes, surprise, surprise, is equal to the coalescent rate. It's equal to 2n to 4n generations, because that's how long it takes to reach fixation and to start building up polymorphisms. And so if you're running a simulation, as a person that runs simulations every day, what you have to do is you start off with no diversity. You run what's called a burn-in period, where you let it reach an equilibrium level of diversity. Now,
and then you go.
And then you start counting, right? Once that population has equilibrated. Since he runs all of his populations, the really small ones and the one that is 10,000 individuals large, for only 10,000 generate, he's run it for 1n generation. He has nowhere near run that simulation for long enough to see any mutations, like segregating. And that's why the percent retained is 0%. He's not reached equilibrium. And so like this, and again, because we expect that into like populations that are really large in size should have a lot more diversity than those that are very small. And that's why this plot makes no sense. It should be backwards. And the only reason that it's shown like this is because he didn't run the model long enough. So he's like completely missing some basic pop gen to not understand that, wow, my small populations have the most diversity. I must be doing something wrong, right? Like this is just very strange to me.
And to be clear, he does talk about in his methods a burn-in period for these simulations. He just doesn't do it enough relative to the population sizes he's using. He uses a uniform, I believe, if I'm recalling correctly, he uses a uniform burn-in for every population size.
He runs them all for 10,000 generations. So he has like a 100, 500, 1,000, 5,000, I think 10,000 are the different sizes.
You can see here, I think you can see on the figure, he's got whatever those points would line up to in there, and then 5,000 and 10,000.
Yeah. So for that 10,000 one, and generally, like the rule of thumb, and since Mendel's accountant doesn't allow you to do this, but simulation softwares that we use do allow you to do this.
Real simulation.
Real simulation softwares, you can actually detect when coalescence has occurred. And so basically once like coalescence has happened and you don't have a bunch of independent lineages that are just like artifacts of the initial starting state, when that happens, the simulation is like, you're good to go, and it'll start recording, right? Mendel's accountant doesn't do this, but it doesn't matter. You can either do that, or the rule of thumb is to wait 10n generations. So, and that's within the upper end of the variance for how long coalescence should take, because coalescence has a large variance. And so if you wait at least 10n generations, then you have more than likely allowed coalescence to occur. So he should have run the simulation of the 10,000 population size for at least 100,000 generations before he started counting. And he didn't. He did not run it for nowhere near long. Nope. That's why this plot just looks so wonky and doesn't make any sense.
I'm once again struck by the fact that in order, to do this work, young Earth creationists would have to have a level of practical know-how in basic population and population genetics analysis, and there is just across the board zero interest in doing the hard work to learn this stuff. And to be clear for everyone, to make it crystal clear what this requires, I am an evolutionary biologist. My dissertation was on mutation accumulation in viruses. Zach has explained these things to me because they were not part of my pre-existing knowledge, despite my background in something very closely related to this. You need to really specialize and really spend years doing these things to then see why, if you run the simulation and you get this kind of distribution, you should look at this and go, red flag, that's wrong. Yeah. That is wrong. And if you haven't taken the time to do that, then you're going to get these ridiculous results. That's
a really good point. So sometimes we take it for granted that when you've been doing simulations for a really long time, you kind of know what the red flags are, you know what to look for. But very often, people don't understand how simulations work. And this is not just I'm not just picking on Carter here. This is lots of biologists that do simulations, and I'll get a paper to review and I'm like, dude, you've made some big errors here. And these are things that should have been red flags you should have recognized. So simulations are hard. They're hard, and it takes a lot of dedication and a lot of effort to be sure you're doing them correctly. And so this is one of those things where it's just a very obvious and basic red flag that you should have known that you are not running your simulation correctly. Also, the linear relationship between mutations and population size is the silliest thing to plot. This tells me nothing. These are neutral mutations, right? You don't have to plot this. It's It's hard coded into the model. It has to produce it. You gave it no choice.
Simplest math. It's the simplest math imaginable.
I don't understand why he felt the need to even plot that at all.
Yeah. And yes, to answer the questions of the people in the chat, this is using Mendel's accountant. That is the model that he uses throughout. And he does reference the Mendel's accountant that's available online. However, you cannot go and try to replicate his work because Mendel's accountant is no longer available online, and we have no time frame for when it will become available again. So that's fun. He did this analysis either, Roop or one of the other people who maintains Mendel's accountant, either gave him a copy and said, this is the version that was available, or he did it while it was available. And it is now, if you go to that URL, no longer available. There are copies floating around, but they're not like the real one, according to Christopher Roop, who's, as I understand it, was kind of maintaining it on behalf of Dr. John Sanford. So we can't go to Mendel's accountant and just do this right now. You can't do it.
Yeah, I've been told, I think it was either Donnie, it must have been Donnie that said that it should, that says that it's apparently now available. I have not messed with it, but apparently there's some way to get it. I don't know how you have
I remember earlier, I want to say in the fall of 2023, it's going to be available very soon. Yeah. And then somebody emailed with Roop and he was like, yeah, no, I don't know. Yeah. So I don't know if that ever actually happened, but as of like last summer, it was not available with no time frame for it to be made available. But I would be happy to be proven wrong because I would love to get some people together and just mess around with Mendel's accountant for a while. That would be very, very educational for everybody involved, I think.
Yeah.
Okay, so I think that horse has been beaten enough. So let us move on just a little bit here. Let's see. We're on page 174. So let me just jump down to 177 because there's a really important line here that we just need to point out. Down here, nearly all mutations are expected to be deleterious. Okay, there's two problems here. And they're kind of like pulling in opposite directions here. So one, he cites Sanford 2014. Sanford is the genetic entropy guy. Sanford, Zach, you have talked at length about genetic entropy. I have talked at length about genetic entropy. It is, as somebody, I forget who said this, but it is population genetics fan fiction. It is just, there's no relationship to like how population genetics actually works. So to cite Sanford, basically, he's just misrepresenting this distribution from Kimura to say virtually all mutations are deleterious. But the other thing here is, Zach, if you have a lot of deleterious mutations occurring in a population, obviously not everybody is going to get the same mutations. Some people are going to get worse ones. Some people are going to get less bad ones. And then what happens when those people compete for resources in that population?
Yeah.
Like natural selection happens.
Yeah, there's this really interesting thing. And so he begins this paragraph, right, with nearly all mutations by evolutionary necessity must be selectively neutral. This was a really interesting way to sort of begin this discussion. And I don't really know where it comes from, because if you look at the distribution of fitness effects in, let's say, bacteria, they're not selectively neutral. Bacteria have very strong selection. Because their genomes look like mitochondrial genomes, right? And that they're extremely gene dense. They're highly functional, right? Bacterial genomes are incredibly efficient things. And so by necessity,
and huge populations, which we'll get to later.
So the vast majority of the mutations in bacteria are deleterious by their nature, and they're selected upon. The key here is that whether or not and again, we're going to assume selection's hard, but the key here is whether or not the individual can pay the selective cost for this strong selection. And bacteria, of course, can. And so I just wanted to there's a little nuance here, and that by evolutionary necessity, like what do we mean? This is variable across the tree of life, what the distribution of mutational effects should be. And there's lots of factors that play into this, including things like how long has a population had to adapt to a given environment, which tells us something about what their distribution of fitness effects should be in the first place, right? So this is like a lot more nuance than what Carter here is putting forward. And even if let's say yet nearly all mutations are expected to be deleterious. If we expect that most populations are well adapted to the environment that they live, that they're sitting on an adaptive peak, then yes, most mutations should be deleterious because they're well adapted to that environment. But again, if they're being pulled off of this adaptive peak, selection pushes them back onto this peak. And this is, again, we observe this constantly. And not only that, but the fitness landscape itself is a changeable thing, right? It's dynamic and it changes through time. And so the occasional pulling you off of that peak is actually not a terrible thing, because it allows you to begin to explore adjacent peaks. So again, that's another thing I have a whole video on.
I think you are giving them way too much credit. I think what this sentence is just you stupid evolutionists, because of your preconceptions about long evolutionary time frames, you know in your heart of hearts that everything would go extinct if there were too many deleterious mutations. Therefore, you have to assume that most of them are neutral. That's all that sentence is. And I think you're giving them way too much credit. Thinking there's some like pop gen rationale for writing that. There is. I don't think there is. I genuinely
that's
don't
probably
think there is.
That is probably
I do want to just highlight our friend Science Side Up over here says, hey, looks like Mendel's accountant's available as of September. I believe that is after the conversations I'm referring to, which means we may be able to access it and play around. And that means we may have some stuff to talk about in the relatively near future. So that will be exciting. Thank you, Science Side Up, for checking that out for us. All right. I am going to skip the right-hand side of page 177 for just a moment. Jump down to 178, because 178 over here, the evolutionary community, blah, 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 they persist in their belief that given enough time, the genealogical and phylogenetic mutation rates will diverge significantly. Basically, if you go back and read here, saying, look, everybody knows that these rates are functionally the same thing, and they persist in their belief for ideological reasons. Now, here's the thing. Creationists know that there are pedigree studies. Forget like long-term kind of phylogenetic calculations that refute this. There are pedigree studies that directly refute this, because we can do pedigree studies in one generation. We can do pedigree studies that span multiple generations. And when they span multiple generations, we see this dropping off in, to use Carter's words, the retention of mutations in those populations. And my friend, Dr. Nathaniel Jeanson, Harvard PhD, actually cites several of these studies looking at for example, populations for the Y chromosome, populations of men that share a known common ancestor 200 years in the past. We also, for example, can look at something like the settlement of the island of Tristan da Cunha in the South Atlantic Ocean, which was uninhabited until the year 1820. And when we look at the rate of divergence in that population, what do we find? We find something much closer to the long-term phylogenetic rate than we do to the single generation mutation rate that creationists love to cite. There was also a great study just a couple of years ago. I think it was based on, I'm going to get the king wrong. I want to say it was Richard II. So that goes back a few centuries. I think it was however many centuries, 4-ish centuries. And basically they had an unbroken lineage from Richard II. So they could say, if Jeanson's math is correct, like we can say, if they don't care about Jeanson, the people who did the study, they don't care. They don't even know who Jeanson is. But we can say, if Jeanson is right, here's what we expect to see. And then we can see that the actual number of mutations that we find is way below that. So like Carter is kind of parroting Jeanson here. But they just cherry pick a couple of studies and ignore the ones that span more than a few generations. And if you use the ones that span more than 2 generations, you end up getting a time to most recent common ancestor that's 10,000 years, 30,000 years, 100,000 years in the past, depending on how many generations you're looking at. It's exactly what you would expect to happen based on natural selection operating and, we'll say, slowing down that rate as time passes, right? It's just very like transparent cherry picking, and I find that very frustrating because, Zach, you know, anyone else who has done any scientific publishing knows, if you try that in a real journal or for a real conference, you will get dinged for it mercilessly.
Yeah.
Like, you can't do that. So I have just that one really good one left to talk about on page 177. Is there anything you want to mention before we get to that really, really fun one?
I quickly, I'll say, because it's just the paragraph or 2 paragraphs just above it on the same page.
Up here?
He says that to the right, he says that wait, are we on the same?
We're on, this is,
I'm
on
just above this page. I think it's actually 177 instead of
Let's go to 177. Here we go.
Yeah. So it says genetic drift is almost irrelevant when considering the mutation load of any given individual. And this is a very curious statement to me. And then he says, thus, due to selection, the long-term phylogenetic mutation rate will be slightly less. Depending on how he's using mutation load. So genetic load is the broad concept that there's some fitness reducing thing due to something in your genetics. Okay, that's genetic load as a broad concept. Within genetic load, there's a lot of other additional load style concepts. Mutation load is one of them, but mutation load is about recurrent mutation in which selection is removing usually a strongly deleterious allele. Okay, that's the mutation load. I don't think that's what he means here. I think he means the drift load here. Because he's talking a lot about effective neutrality and whether or not selection is efficient enough to remove a mutation. The mutation load is always when selection is what's doing the removing. The drift load, alternatively, is when selection is not efficient enough. And the prime problem is genetic drift. Like if the drift load is literally called the drift load, if the drift load is the thing, then genetic drift is the primary problem, right? That's what's preventing populations from adapting. So it's very kind of bizarre to me that he would say, and he would make this whole argument about effective neutrality and then go on to say that genetic drift is almost irrelevant. It's like he's not understanding the words that he's using.
I co-sign that. I don't think he understands several of these concepts. And that leads us right to the next paragraph here, which has my favorite sentence in this whole paper. I was reading this paper, and I got to this line, and if I could have flipped my desk, I would have flipped my desk. Are you kidding me? And the line that I'm referring to is right here. Selection is also more efficient in smaller populations.
I don't.
What are we supposed to do with this?
So you remember we were on Dapper's stream not that long ago. And there was a discussion about whether or not creationists lie or are ignorant, right? That's the potential dichotomy here.
Right.
So what do we think Carter is doing here? What's the play here? I don't understand what the play is. Not only that, okay, it gets.
How do you write that sentence? I want to just, for the audience, just to be clear, I teach every summer. I teach the 200 level intro evolution course, right? And we spend a day on all the major. There's one lecture, it's just natural selection. There's another one. The next one is on genetic drift, right? And one of the big things is we talk about how these things are basically kind of inverse of each other, where if there's one that's doing a lot of work, then the other one necessarily isn't. And Carter was right earlier in this paper when he said that drift is most active in small populations and then diminishes as a driving force as the population gets bigger. That is correct. But then how do you turn around and say selection is more efficient in smaller populations? How do you do that? I award you no points. Yeah. That's all I get. You would get that. That's literally a question on an exam I give, and my undergraduates get it right.
I just, it's so baffling to me.
What are we doing?
It's literally Pop Gen 101. It's Bio 101, to be honest.
I will say it's technically my course number when I do general biology 1 is 115, but we do a day called population genetics, which is we cover 2 basic things. We cover the primary mechanism, the big 5 mechanisms of evolution, and we talk about Hardy-Weinberg. And when we talk about selection and drift, we talk about how selection's most effective on big populations and drift is most effective on small populations, Gen Bio 1, intro bio.
Yeah, so
cover it.
Just because I don't want to sound gatekeepy, and I want to be sure everybody knows why this is so we're so frustrated by this. So I want to explain why this matters so much. So what genetic drift basically does is it introduces variance. It introduces variation, stochastic variation in allele frequencies from one generation to the next, right? And that's just random. It's random noise of which allele gets passed on, right? Selection, however, is deterministic. It's trying to drive a certain allele to fixation. But since drift is random, you have these two alternating processes at work. If the strength of selection, right, is less than the variance induced by genetic drift, then drift is dominating. Now, what determines how much variance you expect to see? The population size, right? So the smaller the population, the greater the variance. You can think about it like a flip of the coin, right? We know that the distribution we should see of heads and tails should be 50-50. If we could flip that coin infinitely number of times, we would get exactly 50-50. If we flipped it 10,000 times, we'd get pretty close to 50-50. But if we only flipped it 10 times, I could get 80% heads and 20% tails. That's a huge variance away from the expectation, right? So that's that increased variance due to drift in small populations that selection can't overcome. It becomes less and less efficient at overcoming the random stochasticity. So that's why, and that's like, again, that's basic. Like I could use the example of a coin flip, right? It's the basic as you can get.
I do the example I use for this is the quintessential, like, you take like AP statistics and you do the thing with like the paper bag with the marbles in it, and you take like 5 marbles and you have to extrapolate the frequencies, and then you pool everybody's 5 marbles together in the classroom, so you get like 50 or 100 or 150 marbles, and now you can accurately determine what the frequencies are because you have a bigger sample size. That's the example I use. It's the same thing. It's you have small population means your random sampling is not going to be representative. Exactly. And you end up with this big variance that selection can't overcome. And like, how does one write a paper on how selection is unable to do a specific thing? And he's mathematically modeling this, how selection has a very specific set of effects on these populations, and he's fundamentally wrong about how selection operates. And like, I don't know how you write that sentence in this paper. I do not understand it.
And also his models show it. So if you go to figure 8, and there's a couple of funny things that are going to happen here. Firstly, is that this is a model of a population size of 100,000 with a mutation rate of 0.05. So just keep that in mind for a second. And what you can see is pretty rapidly a divergence between the neutral number of mutations and the deleterious, right? And that's selection, right? Because he's assuming that I believe that they're equally proportioned, so they should stay the same. But since they're falling off, then that means selection is sort of removing those mutations. Now go down to figure 9. Now, this is a goofy thing that Carter does, and I don't know if he realizes that he did it, but this is for a population size of 10,000 and a mutation rate of 0.005, which actually means, which actually means those things are equivalent to one another. The only difference is that the population size in the previous one is so much smaller and is so much larger, so selection is actually so much more efficient.
So we've got 10. So we've got 10,000 here. We've got 100,000 here.
100,000.
So look at that. No divergence in the small population.
And
big divergence in the big population. Look at that. Selection is operating more efficiently in the larger population.
And it's like literally it's a figure in his paper, right?
That's amazing. I didn't even, as I was going through this, I didn't even catch that the population sizes were different, and that's amazing. I love it.
It's pretty wild. Maybe he'll watch this and then he can clarify and he can like say, oh, well, I meant X, Y. Like maybe there's something that he meant. I don't know.
We know, well, he's been very busy lately cleaning up Jeffrey Tompkins' mess with the human chimp stuff. We know he's been doing a lot of work on that lately. So I don't know if he's going to have time. But Dr. Carter, if you do see this, by all means, pick up that ball and run with it. And even better, come on and chat with us. We would love to chat population genetics with you. That would. You're a geneticist. Zach, population geneticist. I'm not strictly, I mean, my degree says genetics. It says genetics right on it, but
we're all geneticists. We're all geneticists.
So please, Dr. Carter, chat with us. Redo these analyses with the correct parameters, something. Keep doing this, because I would love to see what happens when you do the math correctly, when you've addressed some of the errors that we have pointed out here.
Yeah.
So we've been going for almost an hour and 10 minutes here. What I think we ought to do, Zach, is just take a couple of minutes and just summarize some of the big errors that Carter makes here, like the big ones that this is why these simulations are not worth anything.
Mm-hmm.
And just big picture, why he's wrong about natural selection not doing the thing that he says, not acting the way he says it does, which is to say, doesn't do enough to reduce that rate of accumulation to get us outside of a biblical young Earth timeline. Yeah. So why don't you take just a couple minutes, and then if I feel like there's anything you don't mention, I got a couple of things that I think are worth putting a pin on.
And not to I'll try to stay broad, but there is one thing that we didn't talk about that I think will help bring us back to this sort of broad aspect, is that in all of these simulations, he uses what's called a Weibull distribution. And that's his distribution of fitness effects. And what's very important about this is that he doesn't tell us the shape parameters of this distribution. If you're familiar with mathematical distributions, the one everybody knows is like the normal distribution, right? So it's just like a bell curve where the mean is in the center, and then 3 standard deviations of the mean, you've got 98% of your data, okay? So that tells us something about how many deleterious mutations you expect to find, because they're draws from a distribution, and how deleterious they are. But the shape of that curve, importantly, dictates those things. We don't know what the shape of the curve is that he used. So I can't actually assess whether the shape of his distribution of fitness effects is anything real, is anything meaningful. And I don't know if I should expect selection will be able to be efficient here, because I don't know what the DFE looks like. So this is like a really, really important, fundamental flaw in all of these simulations, is he doesn't tell us what the shape parameters of his distribution of fitness effects are for us to even be able to evaluate if they're realistic. On top of that, all of the mutation rates he uses are way beyond anything that's empirically observed. So he's using rates of 0.05, 0.005 as the deleterious mutation rate, per generation. That is enormously high. That's orders of magnitude higher than anything we observe, right? And so, of course, mutations are going to drive the dynamics, because they're overpowering literally every other feature of the population. So that's just the broadest as I can get as to why these simulations are really bad. And also that he didn't do burn-in. So the bigger population sizes, just discard those. They don't mean anything because they haven't accumulated any amount of diversity.
And just to add on top of that, I'll just kind of harp on how he thinks natural selection works. The combination of, we are using these models with, he describes it as, in effect, hard selection, even though that doesn't quite bear out in his figures, but he, with the words he uses, describes it as, to be selected out of the population is the individual carrying that mutation dies, is how he describes it. Even though the model, it doesn't quite show that, but that's what he describes, which puts kind of an upper limit on the strength of the efficiency of selection, because, as he says, if you have too much selection, then you go extinct because everyone's dying. Well, that's not accurate. That's not how that works. So he's using an artificially low efficiency or strength of selection, however you want to describe it. He's using selection that is artificially ineffective. And that's going to bias his results. And then combine that with this misunderstanding of the relationship between the efficiency of selection and population size, which he shows visually, right? Smaller population, less efficient selection. Larger population, more efficient selection. Yeah. He visually shows the correct relationship, but by not grasping the significance of that relationship, his conclusions are wrong. Yeah. In terms of the ability of selection to cause those two rates to diverge from each other. His big, one sentence argument is selection doesn't cause those rates to diverge. He literally has a figure showing that it does.
And you can see it almost looks like the deleterious rates are going to equilibrate. They look like they're starting to flatten out. which is like sort of exactly what you would expect if if an equilibrium rate was going to be set by selection, given how short of a time that he ran this, and yet it's
because
really starting to flatten.
And like you said, this is 100,000 population, 100,000. You can't just do 10,000 generations there. You need way longer.
It's already starting to flatten.
And it's all right. So if you were to project this out, it would
just
flatten. It would just reach equilibrium, which, by the way, is what every critic of genetic entropy ever has said will happen. It's literally what everyone says will happen, because like it's not complicated math that gets you to that point. Even I understand it.
And that's also just the mutation load. That's just how we define the mutation load. It's just like the persistent equilibrium rate of deleterious mutations, which we know are going to exist in every single population. But yeah, I like to just like go back to like the really, really broad things. Like the false premise is like kind of overturns this at the outset. Like before we even had to get into anything, that whenever that coalescent ancestor lived tells you exactly nothing about when humans originated, right? That's like saying that just because a mutation goes to fixation, whoever was the one where that mutation originated in, that's the origin of species, right? Like that literally makes no sense.
So just to several things that on their own invalidate this. Coalescent time does not equal origin. It's one. Pedigree mutation rate does not equal the neutral mutation rate. Those are two different things. You cannot treat them as identical, which is what all creationists do when they do this, going back to Jeanson. 3, using we'll put it in quotes, hard selection invalidates your model, because that is not how natural selection works in the real world. It's not live, 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 die, live, live, die, die, live. That's not how natural selection works. That invalidates the model. And then the misunderstanding and misapplication of the relationship between population size and drift and selection, that also invalidates what he's doing here. Any one of those things on their own invalidates what is going on here. And we have all of them stacked on top of each other. Dr. Carter, I beg you, clean up this mess, please. Fix it and try again.
Yep. And tell me what shape parameters you use for your Weibull distribution. Thank you.
Yeah. And I think we'll leave it at that, everybody. This has been Dr. Zach Hancock and myself reviewing genealogical versus phylogenetic mutation rates, answering a challenge. I love that. I skipped over a couple places where they were like, some skeptics say, and like I'm one of those skeptics. That's me. Yeah. So this is bad. It's wrong, and Carter has not successfully addressed the challenge that has been made by skeptics of the just Fantasyland population genetics that young Earth creationists use to reconcile the distant time to most recent common ancestor coalescent times for the Y chromosome and the mitochondrial DNA in humans. Those actual numbers are at the most recent 60,000 years, and then for the Y chromosome, it goes out to 200,000 to 300,000 years. Yeah. Obviously far outside the young Earth time frame. That's what we have for everybody tonight. So thank you all, everybody. I appreciate you all being here. Looks like there's, I'm going to put the screen down here. There are almost 90 people here. I can't believe there's almost 90 people here.
Listening to PopGen.
Let's talk PopGen for about 80 minutes. It really does warm my heart. I appreciate all of you being here. Thank you all for being here. Please like this. Please subscribe to the channel. If you've watched this, you're here watching and you're thinking, this is great, I should do this more often. You should subscribe to the channel, and you should subscribe to Zach's channel, which again is linked down in the description. If you haven't hit like already, please hit like. And, share this, leave a comment, and maybe, hey, ping Dr. Carter. Say, hey, these guys talked about your recent paper from the International Conference on Creationism. You should respond to the problems they raised. And we'll see. Maybe we'll get something from Dr. Carter. So that's where we're going to leave it, everybody. Actually, before we go, Zach, do you have anything fun coming up on your channel?
The thing I'm actually have like some job interviews coming up, so that's kind of like pushed back how frequently I've been publishing things, but the project that I am working on right now, the next big thing for the channel is the waiting time problem. I have a script together for it. I have simulations for it. We're going to do the math. We're going to look at some simulation results. We're going to see why there is actually no waiting time problem. And we're going to review the whole history of it. So that's the next big thing that I'm working on. Hopefully, probably middle of February after my interview cycle is done.
That sounds fantastic. I'm looking forward to that. I've covered the waiting time problem. The math that I do, you could do on a napkin. I'm sure your math will be more sophisticated. To be clear, my math shows why it's wrong, but your math is going to be way better than mine. So I'm really looking forward to that and really digging into the details of what's going on there. As for me, I've got a couple videos kind of lined up. I have some conversations that I want to show that were actually from last year. I've got a couple things, conversations I had with our friend Donnie B and his sidekick Raw Matthew, and just that exemplify some of the pitfalls of young Earth creationism when you are not a scientist and you take professional young Earth creationists at their word when they tell you things. So that's I got a couple of those kind of coming up. And I also have I have things planned that some of them are already recorded and they'll appear at some point relatively soon. So with that, everybody, thank you all for being here. I really appreciate how many people are here and the lively chat and everyone just hanging out, having a grand old time. So have a great night, everybody. I hope to see you back here soon for a live show. And I hope to see you all in the chat on Zach's channel when he does stuff. Have a great night, everybody. Goodbye.
Yep.